Okay, welcome everyone to my new lecture where we are going to learn about the magnetic induction, the magnetic flux, and the strength of the magnetic field. Okay, so first, here you have a magnet, and from the north you have magnetic field lines going out of the magnet, and in the south you have magnetic field lines going into the magnet. So here you have a picture, another magnet. Here is the north and here is the south. So something looks like this. It shows these magnetic lines. Now these magnetic lines, the density of those magnetic field lines we call magnetic induction. So here you can see a magnetic induction here also. The magnetic induction, okay, it depends from which distance do you calculate this magnetic induction. And the sign for the magnetic induction is capital letter B, and it's measured in Teslas to a Serbian great electrical engineer. Okay, so these little lines are magnetic, so these not little, are magnetic induction. 1 Tesla is a huge value in magnetism, so usually we calculate the magnetic induction in Gausses. 10 to the minus 4 Teslas is 1 Gauss, I think. But it doesn't really matter. Now, okay, so these lines here are magnetic induction. The density of it also depends from which distance from the magnet you measure them. Okay, so that's the magnetic induction. Okay, the amount of magnetic induction that goes into some area, surface area, we call magnetic flux. Here is the sign for the magnetic flux. This is capital letter Phi. Here you have one line separated, and it's measured in Webers. Here, capital letter W and little b. Okay, so the formula for the magnetic flux is B times A. A is the area. So, for example, you have here an area, and you have magnetic inductions like so. You'll have, this is the magnetic induction B, this is the surface area A. So magnetic flux is gonna be B times A. So if you make this surface area smaller, like so, then you'll see that you will have less magnetic induction going into this surface area. This is very important for my next lectures. We are now learning what is the magnetic induction and what's the magnetic flux. So, then the magnetic flux is how many lines come into this surface area. That's really important. Magnetic flux is very important for generators, for magnetic circuits, for magnetic materials, and so on and so on. Okay, so let me see if we can make okay, so that's it for the magnetic induction and for the magnetic flux. Let's learn about the strength of the magnetic field. Let me just Okay, so here you have the strength of the magnetic field, H. Okay, and it is measured in amperes per meter. Now, what is the relationship between the magnetic induction and the strength of the magnetic field? Well, here we have a formula for that. It's B is equal to mu 0 mu R times H. Mu 0 is a constant. That's the permeability or permittivity. I forget how they say it in English. I think it's permeability of the vacuum. So here you have the permeability for vacuum, and it is mu 0. It is equal to 5p times 10 to the minus 7 Henry per meter. So this is a constant. This is the permeability of the vacuum or air. Here you have a relative permeability of the I forgot how you say it in English. Not of the air, but from some kind of, material. This is the relative permeability of the space or the material in which magnetic induction goes through. How can I say it? For example, iron, water, And it's measured. It also depends on the magnetic material. And it can be 1, 2, 3 dots. It can go to the infinity, but not really. But so the value of this is just 1, 2, 3, 5, 6, 7, 8, and so on and so on. It can be 200. This is the relative permeability of some space, some kind of space. So this is the relationship between the magnetic induction mu 0 times mu r times the strength of the magnetic field. So you can see that H is the strength of the magnetic field is the magnetic induction divided by the permeability of the vacuum and permeability, relative permeability of the space. Okay, so let me just see. Okay, so that's one equation for the strength of the magnetic field. We also measure the strength of the magnetic field of the solenoids. So example, we have a solenoid, I don't know, it looks like this. And so how can we measure what is the strength of this magnetic field where the electric current is going through this circuit? The formula for that is strength of the magnetic field is equal to I times M, capital N, divided by L, and it's measured in amperes per meter. So it's here. So I is the current that will go through this loop, N is the number of loops, and L is length of the solenoid. So here you have the L. This is the length of the solenoid, and these are the loops. 1, 2, 3, 4. And you can make hundreds of loops, even thousands sometimes. Okay, that's okay, so these are all the equations. Let's do one example. Let me just see. I'm gonna remove all this here. Okay, we have to calculate the magnetic flux. So the magnetic flux is equal to question mark. Okay, we have to calculate the magnetic flux that flows through the loops of a solenoid. Solenoid has 300 loops. So this is loops, 300 loops. And its length is 20 centimeters. And that's 0.2 meters that you have to transform into the basic units. The basic unit, SI unit for the length, is meters. Okay? The area of the solenoid here is 8 centimeters squared. That's 8 times 10 to the minus 4 meters squared. And we have a current that goes through this loop with a strength of 0.5 amperes. So we have everything here. So we have a solenoid with 300 loops, length 0.2 meters, and the area 8 times 10 to the minus 4 meters squared. So we can first calculate what is the strength of the magnetic field. So I times N divided by the area, 0.5 times 300 divided by, divided by the L, and that's 0.2. And now you get 750 amperes per meter. So when when there is a current in the solenoid 0.5 amperes with 300 loops and the length of 0.2 meters, you will have 750 amperes per meter. So let me just. So now we calculated the strength of the magnetic field. Now we can calculate the magnetic induction. That's equal to mu0 mu r times h. So mu r, because it's now in the air here, is equal to 1. So the relative permeability of this in in the space where this is, it's in a vacuum. Solenoid is in a vacuum or in a air. So the relative permeability for the air is 1. Now you have 4 pi times 10 to the minus 7 times h is 750. And you get a really small number that's equal to 0, 0.0000937 Tesla. So now you can see that the magnetic induction here is relatively small. So what do? We always put an iron here. So this relative permeability will be, for example, 200, and then you will get a higher magnetic induction. That's why, you know, car construction factories, when they move one car to the other, they put the solenoid on an iron, for example. And then, let me just... So we can now calculate the magnetic flux. That's equal to B times S. Oh, sorry, in my language we use S for a surface area, but in America and England I think you use A. So this is B times A. B is this, I'm not going to write it, times A to the minus 4, and then you will see that you get 0.60. Is it 60? 75 Webers. So you can see this is a really low value and you can't do much with it. Okay, so we did one example. That's all for this lecture. Let me just explain one more thing. So now you see here that the higher you have, if you put a higher current, that you will have, I don't know, you have a stronger magnetic field. And if you put, I don't know, 50 currents here, you'll get, I think, 750 amperes per meter. But what is the problem with magnetic materials? Some magnetic material, so if you put an iron here and you put around a solenoid, and then this becomes N and this becomes S, I don't know. Yeah, so if current goes in this way, yeah, this is going to be N and then S. This is going to be north pole of the magnet, this is going to be south pole. So an iron that isn't a natural magnet, but it can be an artificial when you put solenoids around the solenoid around through the or on the iron, this will become a magnet. But as you can see, there's a problem. You think, yeah, well, if I put more current, higher and higher current, that this is going to be some kind of strong supermagnet. No, every material has a point when you can't add more. You can add really a lot of current, and then you will have a strength of the magnetic field. But it can only have a certain amount of magnetic induction. So there is a maximum point that any electromagnet can act as a magnet, or any ferromagnetic material can act as a magnet. For example, here if you put on an iron, I think, so this is the H scale and this is with the B scale. The B is measured in Teslas, and for you have 2, 1, 0, and here you have 500,000, and so on and so on. So, for example, when you have 500 amperes per meter, you can have, I don't know, 1 Tesla. We are now talking about some magnetic material, I don't know. When you have 100, then you have, for example, 1.5. And if you put, I don't know, 3,000, then you will have 2 Teslas. But if you add more and more, you can't make this, you can't make it go on and on. So every magnetic material has a maximum value. That's not, I mean, it is important, but I just, not really, because I'm teaching you the basics of electrical engineering. I don't want to, make you learn some harder and more difficult stuff. I'm gonna do that for college physics and college electrical engineer when I make those cars. So, that's it for this. This is gonna be, more important throughout my next lectures. Thank you for watching and see you in my next video.